functions. So you can write your own tools where you would be the one writing the skin here, and you perform some kind of instrumentation. So sometimes you want to write your own custom instrumentation, and so you can use Valgrind for that. But oftentimes using Valgrind is too expensive. And there's another technique here that I'd like to briefly touch on that allows you to write your own custom instrumentation. So sometimes, let's say, you want to know when is a particular function invoked in a given program. Maybe you want to write a tool that can say when a given function is invoked, even for executables that were created by someone else. And one such method is the use of LD preload. Now, LD preload is an environment variable that you can set that controls the functioning of the dynamic linker. I can give you one example here. This is an example from our OS course. In the first assignment in the OS course is to write a simple simple thread-safe memory allocator. And so this is for a lot of students their first exposure to locking, and they end up making mistakes such as forgetting to unlock a lock that they are holding. And so in a correct program, they would be called lock, unlock, lock, unlock, would be paired. They make a mistake, they call lock, forget the unlock, then they call lock again. And the question is, how do we detect that, right? So one way is to just print out whenever they call something, print out something whenever they call lock, print out something whenever they call unlock. And if you look at the output, they see two locks in a row. That's the problem. I'll show you what that looks like. So for instance, if I say, I'll show you how LD preload in action. So you set LD preload. Let's say I'm setting it to point to this particular shared library here. And then I'm running my test code. I'll pipe the output. So if I run this, I say, okay, mutex lock called here, and that's the stack trace. Then mutex unlock is called, that's the stack trace. Lock is called, unlock is called, and so on. Okay, so things seem to be going fine, and no deadlock. Let's say I am doing, we're introducing a bug. Okay, this is my sample solution. Let's say I'm putting in a bug whereby I forget to call unlock here. Okay, so this is my code here. I call lock, and goes through this, and then before I return, I call unlock here. Let's say I forget it here. Okay. So if I run this program now, and I run it again with the same LD, what will happen is the output will show mutex lock on this call path, mutex lock again, and then it gets stuck. Okay, it gets stuck. Why? Because boom, it's deadlocked. I call it, getting a lock, trying to get the same lock again, I can't. Okay, so easy enough to use, and let me show you how this is done. So what I've done here is I've created a shared library, and I set the environment variable LD preload, and I told the Linux shared linker to load that shared library before it to load it first, before the other shared library on which this program depends are being loaded. LDD is used to show what shared libraries it depends. So this one depends on these libraries here, but in addition we say let's load this one first. Let me show what this shared library looks like. It's 98 lines of C code, and this is the shared library here. Okay. Specifically, it defines two functions: pthread mutex lock and unlock. So those are the functions that the program codes. So the standard pthreads, POSIX, lock, and unlock functions. I'm defining my own here, okay? And I tell LD preload, load this shared library first. So that means when the test mem executable loads and needs to dynamically link against those pthread mutex lock and unlock function, it will pick up mine, not the ones from the system. And so, okay, so it loads those, and what I'm doing is I'm calling init, and then I print out this message that says, okay, pthread mutex lock was being called. I'm also printing out a backtrace, you've seen that. And then I am calling underscore pthread mutex lock, which is the actual pthread mutex lock function in the actual pthread library. Now all I have to do is I have to make sure that I can reach that function using these variables or these function pointers, pset mutex log and unlock. And this is done in the init function here. So in the init function, I am dynamically loading the actual pset library. I am looking up in that library the addresses for these symbols, mutex log and unlock. I'm recording the addresses in these function pointers, and then when the user program calls the overridden functions that I've provided, then I'm using this function pointer to call the actual function after I've printed this output. So this is shown here. So I print this output, and then I call the actual function to make sure that the mutex is being logged. And so just as a reminder, this is the output here. Pset mutex log is called, outputting this, outputting a backtrace, log is called, and I'm actually deadlocking because I am calling the actual function in the pset library. So this is a way to interpose, and you can use that for log unlock. You can use that for things such as open, read write. For instance, you can make it so that when file name is being passed to open, you first examine that file name, then decide whether to go ahead with the open or not. So you can use it for a number of interposition tasks, for debugging, but also for other features. Questions, thoughts? Is that well known? It only works for dynamically linked functions. Okay, if it's a function in the executable, this technique will not work. Related to that is a command called strace. Okay, the strace command is a command by which you can monitor a process and you can trace what system calls it does when it calls into the kernel to get a kernel service. And so here, for instance, I can say strace, I know strace bin ls, and I'm getting an output that shows me each system call that's being made. Name of the system call, the arguments, and the return value. So for instance, it calls execve, bin ls, and then a number of system calls that relate to the shared library loading. So it loads various shared libraries here, maps them into the address space, and so on. And this can be useful if you need to understand what how a process interacts with the operating system. In particular, for instance, if you have a program, the program says file not found. I'll show you an example. Say I made this mistake here. Suppose I do this. Okay. It says object lib verbose log from ID preload cannot be preloaded ignored. Why not? Well, let's run strace and let's see what it was trying to do. So if I run strace here, then I see that verbose log, look for verbose log. So what it's trying to do is it tried to open libtls, lib verbose log, lib this, and all these failed because this file doesn't reside in that directory. And then eventually it gave up. And from that I learned that apparently the dynamic linker doesn't look in the current directory unless you specify it. So the correct way of running this is with /libverbose. Okay. So if you don't, in other words, if you don't specify a path here, it will only look in a set of directories that is dictated by the system. If you don't know that, use strace. Strace tells you exactly what system calls it does, what it asks the operating system for in terms of what files it wants to use. You can also use strace to attach to a currently running process. So the process is interacting with the system in some way. If you want to start tracing system calls, you can do that as well. Now to GDB. Okay, I'm really uncertain what to tell you about GDB. It's really a traditional debugger. There's a command line version. There are some front ends. DDD is a particular front end that's used in Linux world. Now GDB is designed to run in a number of environments. I should mention that. GDB can be used, of course, to debug user-level programs. In this case, it starts the program in a separate process, then it